Welcome back to the Deep Dive, the place where we take stacks of complicated source material and turn them into crystal clear, immediately useful knowledge just for you. If you've been following along with our previous dives, you know we've covered the essential foundational infrastructure of the cloud. But today, we are taking a massive step forward. We are moving firmly into intermediate and, frankly, expert territory. We are diving into the absolute non-negotiable foundation of any serious, scalable, and compliant cloud environment: identity and security architecture.
It's the next logical step. It really is. Anyone working in this space today quickly realizes that security isn't just a static bolt-on or a checkbox on a deployment checklist.
Right.
It's no longer enough to just rely on a virtual firewall at the network edge. When you scale up, security becomes about governance, managing data lineage, managing identities that could be accessing resources from a dozen different countries, and, ensuring continuous compliance across a sprawling, complex hierarchy of resources.
Exactly. And that complexity is where people get stuck. When they first encounter cloud infrastructure, they might have this sort of fuzzy idea of what things are. They know IAM exists, but maybe they don't know why permissions inherited from the organization level are so dangerous.
Or they've heard the term zero trust thrown around.
All the time.
Huh.
But they don't know the exact mechanism, the IAP and access levels, that actually enforces it. So today, our mission is to move past those fuzzy ideas. We are diving deep into the concrete tools that secure the most complex operations.
Tools like Cloud DLP for data handling, VPC service controls for drawing those hard security lines, and all the advanced nuances of the IAM hierarchy.
So by the end of this deep dive, you won't just know what these services are.
You'll understand why they are essential architectural requirements. That's the goal. Understanding the governance structures and the specific architectural constraints moves security from being a reaction to an incident and makes it a proactive, intentional design element that saves massive time and cost down the line.
Okay, so let's get into it. We have to start where the risk is highest: the data itself. If identity and access management is about who holds the keys to the castle, well, the data is the treasure inside that castle.
That's a good way to put it.
And when you're dealing with highly sensitive data, especially PII, personally identifiable information, the first essential line of defense is data loss prevention, or DLP. What is the primary mission of DLP in this modern cloud context?
Well, the core function of DLP is a cycle of three things. First, it's discovery, finding sensitive data wherever it lives, whether that's sitting in a storage bucket that was misconfigured or accidentally logged in a database field somewhere it shouldn't be.
Finding the needles in the haystack.
Exactly. Second is classification, understanding exactly what that sensitive data is. Is it a social security number, a credit card number, a medical record? DLP has pre-built detectors for hundreds of these.
And then the third step.
And finally, the third step, protection, which often means sanitization, redaction, or de-identification. DLP gives you the programmatic eyes to see the sensitivity and the automated hands to fix it.
That protection part is where we really move into the intermediate architectural concepts.
Yeah.
We have a great use case here, which is all about sanitizing data in flight. So let's set the scene. You are a large data analysis team. You are receiving continuous streams of raw data from an external partner. Maybe it's aggregated sales data or customer behavior data. Crucially, that raw stream contains PII.
Right, a very common scenario.
You need to process this stream and store the results in BigQuery for fast analysis, but your compliance requirements strictly forbid storing that raw PII data in your final analysis warehouse.
This is a classic compliance scenario, and it is a critical architectural checkpoint. The primary goal is to establish a data lineage that proves you never allowed the sensitive data to touch your main persistent storage infrastructure in its raw, identifiable form.
So if you fail this,
your entire BigQuery environment could fall under strict regulatory scope. PCI, GDPR, you name it. It's a huge problem.
So relying on a simple batch job that runs once a night to clean the data after it's already been stored for a few hours is, well, it's fundamentally insufficient and non-compliant. The data must be cleaned before it lands.
Precisely. The solution requires integrating a high-throughput processing step directly into the data ingestion workflow. The recommended architectural approach is to create a data flow pipeline to retrieve the data from the external sources.
And Dataflow is perfect here because it's built for streaming data at scale.
It is, but the crucial intermediate step is integrating the Cloud DLP API into the pipeline itself to remove any PII data. Only after the DLP API has scrubbed the data stream do you push the resulting sanitized record into BigQuery.
What's fascinating here is that the DLP service isn't just a separate scanner you run later on your storage.
No, not at all.
It is integrated as a step right into the processing vehicle. It's like installing I don't know, a required decontamination chamber on a subway line.
That's a great analogy. Data flow acts as the vehicle carrying the data stream, and the DLP API acts as the scrubbing station that enforces your policy immediately. By the time that data arrives at its final destination in BigQuery, you have a defensible, clean, final dataset.
And that ability to process data in flight using programmatic security tools, that really feels like a hallmark of modern, proactive cloud security architecture.
It absolutely is.
Okay, so now let's push this to the next level of complexity. What if removal isn't an option? Sometimes you need to obscure the data for security, but you still need the capability to unobscure it later. This brings us to a vital distinction: masking versus tokenization.
This is a scenario where we shift from PII removal to PII substitution, and the terminology is critical for any security architect. Let's stick with the scenario of ingesting data, but instead of external data, let's say you are ingesting millions of customer support chat logs. Yeah. These logs inevitably contain credit card numbers or other sensitive identifiers. You must mask this sensitive data before it hits the disk for everyday security analysis. But a potential future event, maybe a legal proceeding, a complex customer dispute, or a court order, might require you to re-identify the original user and their card number.
My first instinct, if I was trying to secure it simply, would be to use simple hashing here. Why can't we just use a strong one-way hash like SHA-256 on the credit card numbers? That's fast and certainly secure, right?
That is the classic mistake that separates essential security knowledge from intermediate knowledge. It really illustrates the difference between irreversible obfuscation and reversible de-identification. Hashing is a one-way street.
A one-way street.
Think of it like a guarantee of uniqueness and integrity. If you take a physical document and run it through a shredder, you can mathematically prove that the shredder produced that specific pile of confetti. That's the hash. But there is no way, no matter how powerful your computer is, to reconstruct the original document from that confetti.
So we know the original credit card number existed, and we have a reference point, the hash.
Yeah.
But the original content is functionally gone forever.
Exactly. Hashing provides integrity and proof of existence, but zero utility for retrieval or re-identification. If we hash the credit card numbers, we could analyze trends based on the hash value, but we could never recover the original number, making it useless in that required legal re-identification scenario.
So for this specific use case, where you must be able to reverse the masking, you absolutely need tokenization, de-identification.
You do.
You used the secure locker analogy earlier. Let's expand on that a bit.
Sure. Tokenization fundamentally involves replacing the sensitive data, the credit card number, with a cryptographically generated identifier, which is the token. The token itself is just a random string of characters and is meaningless by itself. But that token is generated using a specific secure cryptographic key, which is stored entirely separately in a secure vault.
So the credit card number is the valuable item you put into the locker.
Right.
The token is the locker number that you write down on your chat log analysis sheet. And the cryptographic key is the secure key that lets you open the locker to retrieve the original content when absolutely necessary.
And that key is protected by serious controls, often within a key management system, which I'm sure we'll cover later. The solution in the cloud environment is to use Cloud DLP to tokenize, to de-identify the data with that cryptographic key. This setup ensures the operational data lake stores and analyzes the tokenized data, which drastically reduces its compliance burden, while preserving the ability to retrieve the original PII when necessary, but only under the strictest, most authorized conditions.
It's a crucial intermediate concept for modern data security architecture because it balances that utility with protection. It's not just hide it, it's hide it intelligently.
That's a perfect summary.
Okay, so moving from the data to the people and the systems accessing it, we arrive at the foundational architecture layer, Identity and Access Management, or IAM. This system is deceptively simple in its definition. It defines who the identity can do what, the access on which resources.
Deceptively simple is the right phrase.
But once you introduce corporate scale, organizational complexity, and rapid growth, that simplicity skyrockets into a complex governance challenge.
Absolutely. The structural complexity is directly tied to the governance hierarchy that every security architect must master. If you don't structure your IAM correctly from the start, you create massive technical debt, security holes, and just operational headaches down the road.
Let's review that mandatory structure quickly for our listener. It starts at the top with the organization. which conceptually represents the whole company, the highest point of authority.
Mm.
Below that, we introduce folders for organizational units, departments, or environments like production, staging, and development. And finally, at the bottom, we have projects, which is where the actual resources live, the VMs, the BigQuery tables, the GKE clusters.
And this structure governs the most important rule of IAM, the policy inheritance rule. Understanding this rule is the difference between a secure hierarchy and an unmanageable mess. The effective policy at any node, whether it's a folder or a project, is the union of the policies set directly at that node and all policies inherited from its ancestors.
The word union is key there. It means everything that is true above remains true below. We can't subtract permissions, only add them. Let's use the company handbook analogy again, but deepen it a little.
Okay. So the organization policy is the strict company-wide handbook. Rule number 1 is no one, under any circumstances, may delete core financial documents. That rule is applied at the organization level.
So it applies everywhere.
Everywhere. Now, a folder representing the engineering department adds a specific rule. Engineers can deploy code to any project within this folder.
The effective policy for a developer working inside that engineering project is then both of those rules. They can deploy code, and they are still forbidden from deleting core financial documents. The department-level folder cannot set a policy that removes the company-wide rule.
That's right. It's always the union, which means permissions granted at a higher level, especially at the organization level, are effectively granted everywhere below them, which is precisely why those top-level permissions must be managed with extreme paranoia and caution.
It's a huge footgun, isn't it?
Yeah.
One overly broad role granted at the organization level can instantly override all the careful restrictions you set at the project level.
It's the biggest footgun in IAM. It happens all the time.
That immediately highlights the need for structuring for minimal maintenance, which is a key operational goal. When you have 5, 10, 50 departments, and they each need their own segregated environments, and their members all have the same responsibilities, well, manually managing access for every single project that spins up and down is an operational impossibility.
It creates administrative chaos. I remember early on, before we enforced this structure, having to manually update IAM bindings on 40 or 50 different projects when a single developer left the company. That manual process is the pain point the structure is designed to eliminate.
So you need centralized identity management married to decentralized permissioning.
Exactly.
So how do we architect that combination efficiently?
The recommended best practice is to leverage the folder structure alongside Google groups. It's a very powerful combination. You should create a Google group per department, for example, sales engineering at corp.com-ward, and add all employees of that department to it.
So HR handles that part.
Right. Identity is managed centrally. Then you create a folder per department in the hierarchy. Finally, this is the key, you grant the required IAM permissions, the roles, to that group at the folder level. All of the department's projects are then housed under that specific folder.
The elegance of this solution is powerful, both for HR and for the cloud operations team.
It is twofold.
Okay.
First, identity management is centralized and streamlined. HR adds or removes an employee from the Google group, which is a simple non-cloud operation, and their cloud access is instantly managed by the group's IAM policy. Second, the scalability is inherent.
Right.
Because the comprehensive IAM policy is set at the folder level, any new project created under that folder automatically inherits the correct access for the entire department, requiring zero manual intervention from the cloud admin team. It's the definition of a low-maintenance governance model.
Perfect. Now, let's push this governance model to the highest level, an expert scenario. Structuring environments for production versus development, where you need centralized policy management but absolute hard restrictions on what developers can touch in the critical production environment.
This is the architectural pattern for mature, regulated organizations. The core demand is agility for development teams, but ironclad, non-negotiable control over production. A common mistake here is trying to achieve this separation solely through complex role definitions on a single project list. That quickly becomes unmanageable.
So the separation must be structural, based on the hierarchy we just discussed.
Exactly. The foundational structure must be segmentation. You start by creating two separate folders under the organization, development and production. This segmentation provides the clean structural break you need. You might also create a separate shared services folder for things like networking or central logging, but for access control, these two folders are the key segregation points.
And once we have that physical separation in the hierarchy, We apply the access controls strategically.
Correct. You grant developers the project creator IAM role only on the development folder. This gives them the sandbox freedom they need. They can spin up projects, tear them down, test new features, break things, all without any risk to the business. This flexibility fuels innovation.
And the production folder, meanwhile, is locked down.
It's secured by inheritance and explicit policy. Yes. You set general organizational policies at the top for things like billing or required naming conventions, which apply to everyone. But then you apply much more restrictive, explicit policies on the production folder. For instance, you might restrict who can deploy, who can modify the billing settings, or even restrict who can view sensitive logs, limiting those privileges only to a small, vetted operational group.
Okay, let's play this out. What if a developer, purely by accident or through a badly managed group, happens to acquire a broad role like project viewer at the organization level? How do we ensure they still can't impact production? We don't rely solely on restricting their role on the production folder, do we?
We don't. That's a great question. We rely on the principle of least privilege segmented by environment. We manage the developer's ability to create and modify projects specifically within the development folder. The production folder itself has highly restrictive roles applied to it. And crucially, those roles are scoped to specific non-developable Google groups, like production ops at corp.com.
So the production folder has its own set of groups.
Exactly. This ensures that even if a developer has residual broad viewing rights inherited from the organization, their ability to perform destructive or modifying actions is completely blocked by the explicit, highly restrictive policy set on the production folder. This structure makes the separation of concerns extremely clear and leverages the hierarchy rule perfectly to manage risk.
Brilliant. Okay, so security isn't just about setting the policies. It's about proving to yourself, your stakeholders, and external auditors that you followed them. This is where auditing and log visibility become essential.
Absolutely, the prove it step.
If an auditor comes knocking demanding proof of access, you need pristine searchable records of every access and every policy change.
And the challenge often starts right at the source, how logs are collected. We have two very different categories of logs we need to manage, and they require different approaches for collection. Platform-level audit logs and operating system-level system logs.
Let's start with the platform level, the audit logs. If I want to track who changed an IAM policy binding or who launched a BigQuery job that touched PII data, what logging setup do I need?
For these actions, which we categorize as admin activity logs, you technically don't need to do anything. Stackdriver, or cloud logging as it's called now, automatically collects admin activity logs for most services.
It's just on by default.
It's on, yeah. These logs track administrative actions, API calls, metadata. The platform guarantees these logs are captured as part of its operation, adhering to regulatory requirements right out of the box.
So platform logs are inherent to the cloud API itself. But what about the nitty-gritty inside-the-box stuff? I mean, application behavior, operating system kernel logs, system crashes, or third-party agent output from my compute engine VMs.
Those are VM system logs, and they represent the internal state of your managed operating system. They're not collected automatically by the platform because they're inside the abstraction layer. This is a common operational pitfall. To collect those specific logs from compute engine instances, the Stackdriver logging agent must be installed on each individual instance.
That's the operational headache right there.
Yeah.
If you have 500 VMs, you have to ensure that installation and maintenance process is robust across every single one. It's not sufficient to install it on a single log aggregator instance, is it?
Absolutely not, no. Each VM must have its own agent to properly capture and pipe those specific operating system events and application logs back to the centralized cloud logging interface. Furthermore, the installation has to be part of the VM provisioning pipeline using configuration management like Ansible or deployment managers. Otherwise, you end up with compliance gaps and inconsistent log capture across the fleet.
That distinction platform logs are inherent. OS logs require an agent. That's really essential knowledge.
It is.
Okay, so once we have all this data collected, it quickly becomes overwhelming. Let's talk about the auditors again. They visit annually and demand to review all IAM policy changes over the previous 12 months. Sifting through petabytes of raw JSON log files for that much data sounds like a nightmare that takes weeks of engineering time.
It is a complete nightmare. Raw log data, especially after a year, is a vast ocean of unstructured JSON documents. Trying to run complex, long-range trend analysis or even simple filtering on raw log files is extremely slow, inefficient, and costly in terms of labor hours. You need a fast, analytical tool designed for massive historical data.
And here's where the right architectural choice enables operational efficiency. The solution here is to enable logging export to Google BigQuery and use ACLs, access control lists, and views to scope the data shared with the auditor.
BigQuery is the key enabler because it turns unstructured logs into a structured, queryable database. BigQuery is purpose-built for fast, analytical querying of massive, evolving datasets, which is exactly what audit logs are. By exporting the logs, you transform months of history into a dataset you can query using SQL in seconds.
And the architectural benefit isn't just speed, it's control.
Exactly. When the auditor arrives, you don't hand them the keys to your entire logging system. You create a specific limited view within BigQuery that only shows the columns and rows relevant to their request. For instance, only the records showing IAM policy update events.
So you're giving them blinders.
You are. And then you use granular ACLs to grant the auditor access only to that specific view for a limited duration. This dramatically streamlines and expedites the entire audit process while maintaining strict security boundaries around your proprietary data. It's the optimal solution for regulatory reporting.
Let's shift our security paradigm. For decades, the perimeter was king. We built a secure castle, and everyone inside was trusted. That network-centric model is obsolete, especially with cloud, mobile, and remote work. The new, mandated standard is zero trust.
Zero trust means absolute vigilance. Trust is never assumed, even for internal employees sitting at their desk. Every single request for access, regardless of where it originates, must be authenticated, authorized, and continuously monitored. The user's network location alone, are they on the corporate network, is entirely insufficient.
We have an expert-level scenario that perfectly illustrates this paradigm shift. We need to grant access to an internal web application only to employees who meet very specific criteria. They must be using a corporate managed device ANDB located in the headquarters office. And we must achieve this without relying on an old-school VPN connection.
That's the perfect zero trust problem statement.
How do we enforce that granular level of context in a modern environment?
We must combine identity verification with granular context verification. The technology to achieve this highly specific enforcement is the combination of Identity-Aware Proxy, IAP, with access levels, which are managed by Access Context Manager.
Okay, let's break down the layers, starting with IAP.
So IAP handles the identity piece. It sits logically in front of the application, intercepting all requests. It verifies the user's identity against your central corporate directory, like cloud identity. If you're not a recognized employee, the request is blocked immediately. IAP effectively turns your application into an identity-protected resource rather than a network-protected one.
But IAP alone only knows who I am. It doesn't know where I am, or crucially, what device I'm using. That context is the core of zero trust.
That's where access levels come in. Access levels, defined via Access Context Manager, check the context of the request itself. They can check policy attributes like the source IP address to ensure you are physically at HQ's external IP range, the region, and critically the state of the device.
What specifically does state of the device mean in this context?
It means verifying that the device meets corporate security posture requirements. Does it have an up-to-date device certificate installed from your enterprise management tool? Is the hard drive encrypted? Is the operating system patched to a certain level?
I see, so it's a posture check.
It is. IAP only grants access if the user's identity is verified. NDD, the request context satisfies the specific criteria defined in the access level. This moves the enforcement point from the network perimeter right to the application door, fulfilling the zero trust mandate by enforcing identity and posture.
That is a phenomenal example of policy enforcement based on context.
Yeah.
Now, shifting focus slightly to managing the identities themselves. How do we handle companies that are born in the cloud versus those integrating with existing on-premises systems?
For a cloud-native startup with no legacy infrastructure, the solution is simple and clean. Cloud Identity, or Google Workspace, is the central source of truth. This manages all user accounts natively in the cloud and provides the crucial ability to enable single sign-on SSO for third-party SaaS applications like Salesforce or Slack. It is the centralized hub for identity management.
But the reality for many established enterprises is that they already have a decades-old entrenched on-premises Active Directory. Their security team does not want to manage two-password systems, and user disruption is highly unpopular.
Then we federate. Federation is the architectural compromise that provides security, compliance, and user comfort. We use Google Cloud Directory Sync, GCDS, to synchronize the existing Active Directory usernames and groups into Cloud Identity. Note, this doesn't sync the passwords, just the identity records.
Just the user list, basically.
Right. Then we configure a SAML 2.0 single sign-on.
So federating authentication means that when a user attempts to log into Google Cloud, Google doesn't check its own internal database for the password. Instead, it redirects that authentication request back to the existing Active Directory domain controller, the identity provider.
Correct. The user enters their corporate password once, it is validated by the on-premises system they already trust, and a successful SAML assertion is sent back to Google, granting them access. This satisfies the security team by ensuring their existing identity provider remains the source of authority, and it ensures minimal user disruption because they don't need a new set of credentials. This is the operational standard for hybrid environments.
Let's discuss a critical governance constraint now. Security absolutely requires prohibiting IAM users outside the company's domain from gaining permissions. For example, ensuring no one from a random personal Gmail account or a contractor's domain can accidentally be granted access to a production project.
You have to prevent this at the highest possible level to stop configuration drift. This must be an organization policy to restrict identities by domain.
Why is this better than simply educating administrators not to add external emails?
Because education fails, and human error is the #1 cause of cloud breaches. It just is. This organization policy acts as a hard, non-negotiable filter. It locks down who can even be considered for an IAM binding across the entire organization. Structure folders, projects, everything. If an administrator tries to add badactor@gmail.com to a project's IAM list, the organizational policy will reject the request outright, overriding the administrator's ability to make that mistake.
It's an indispensable top-level security guardrail.
It really is.
Finally, in this section, let's discuss one of the most expert-level authentication patterns we have: cross-cloud resource access without shared static keys. This is the power of workload identity federation. Our scenario: an application runs on AWS and needs to read a BigQuery dataset located in Google Cloud. We absolutely must avoid the massive security risk of managing and rotating long-lived Google Service account keys stored on the AWS side.
The standard, insecure way would be to create a JSON key file for a Google Service account. Upload it to the AWS workload, and treat it like gold. That key is long-lived and provides powerful access to your Google environment. If that key is leaked, the breach is catastrophic.
So workload identity federation bypasses the need for that dangerous physical key entirely. It is, as you called it, the diplomatic handshake between the two clouds. How does this process actually work step by step?
It relies on a high degree of trust and standardization, things like OIDC and SAML. The AWS workload uses its own native short-lived credentials, typically an AWS IMM role or a Kubernetes service account, which AWS itself manages and rotates automatically.
So the AWS application presents its own ID card, essentially.
Exactly. Workload Identity Federation is configured to allow that AWS credential to be presented to Google Cloud. Google verifies its validity through a trusted connection established between the identity providers.
And upon verification,
Google Cloud, instead of granting persistent access, issues a short-lived temporary Google Cloud credential back to the AWS workload. This credential is valid only for minutes or hours, and it's scoped exactly to the BigQuery access needed.
So the AWS application never stores the powerful, long-lived Google Service account key. It presents its own ID, gets a temporary day pass from Google, uses the BigQuery resource, and the day pass expires shortly thereafter.
Precisely. The key material is never stored in the foreign environment. It eliminates the security risk associated with static credentials, vastly improving the security posture and eliminating the operational burden of manual credential rotation. It's not just a nice feature, it is the modern mandate for any highly secure cross-cloud communication.
Okay, we've established who gets in and how they prove their identity. Now let's talk about the next layer: governance. The rules we enforce on the workloads themselves, specifically the code and artifacts we run. We need controls that ensure the code we deploy meets our quality and security standards.
If you are running containers, the ability to run code is a privilege. And in secure, regulated environments, that privilege must be earned by passing specific checks. This is the domain of binary authorization.
Let's define the scenario. We must ensure that only container images that have been scanned for vulnerabilities and digitally signed by the QA team can be deployed to a production GKE cluster. That scanned and signed part is mandatory.
That requirement, scanned, signed, and enforced, is the core definition of binary authorization. It is a mandatory access control for the deployment process. It establishes a hard date. Before the GKE cluster will even attempt to pull and run the container image, binary authorization checks for the required attestations.
Walk us through the life cycle of that attestation. Sounds like there are multiple actors involved.
There are. First, the developer builds the image and pushes it to artifact registry. Second, an automated process, perhaps a security scanner, runs a check. And if it passes, it creates an attestation, which is effectively a cryptographically signed statement that says, I, the scanner, approve this image version.
Okay, so that's the first signature.
Right. Third, the QA team manually reviews the results, and if satisfied, they sign the image with their unique cryptographic key. That signature is the final attestation.
So the QA team is the ultimate attester. They provide the final cryptographic proof of quality.
Exactly. When the deployment command comes to the GKE cluster, binary authorization intercepts it. It verifies that the required attestations, the scanner's signature, and the QA team's signature are present, valid, and match the policy. If the image lacks the signatures, or if the signatures are invalid or outdated, the deployment fails.
It fails regardless of whether the user initiating the deployment has full permission to operate Kubernetes.
Completely regardless. It enforces workload integrity before execution.
That's incredibly powerful. But I can hear the developers listening now groaning. It sounds like a lot of friction added to the deployment pipeline.
It is intentional friction. Security inherently adds friction. However, you trade minor operational friction, that pipeline step, for massive risk reduction, preventing vulnerable, non-reviewed code from ever touching production. Binary authorization moves security accountability earlier into the development process, a key component of DevSecOps culture.
Switching to data compliance, let's tackle the complexity of PCI DSS, the payment card industry data security standard. If your application processes credit card transactions, PCI compliance kicks in, and the requirements are notoriously complex and resource-intensive.
Oh, they are?
Our core architectural goal is to achieve the smallest scope of PCI compliance possible while retaining the ability to analyze transactional data.
The scope of PCI compliance governs every system, network, and application that stores, processes, or transmits cardholder data. If your BigQuery data lake or your core analytics platform contains raw card numbers, that entire environment falls into scope, meaning constant auditing, stricter change control, and massive cost.
So the most effective architectural strategy is to remove the raw data from that scope entirely.
Absolutely. The architectural solution must be to create a dedicated, isolated tokenizer service and store only tokenized data in your primary data lake or analytics platform.
This sounds simple, but the implication for the business is huge.
It's a brilliant strategic move. If your massive data lake, your analytics platform, and your reporting systems only contain the non-sensitive tokens, they are entirely out of the stringent PCI compliance scope. Only the small, isolated, highly secured tokenizer service and its associated key management infrastructure remains in scope.
So you shrink the compliance boundary.
Dramatically. From dozens of systems to perhaps 3 or 4. This narrows the governance, auditing, and maintenance burden, saving significant time, complexity, and ultimately capital.
It's a powerful architectural reason for tokenization beyond just re-identification. It's a compliance reduction strategy.
100%.
Next, let's address GDPR compliance. When a web application must comply with the General Data Protection Regulation, what is the technical architect's primary responsibility? Is there a magic GDPR switch in the console that solves everything?
That is the most dangerous misconception in cloud compliance. Absolutely not. This reinforces the concept of shared responsibility. Google Cloud provides secure infrastructure and GDPR compliance for the underlying platform, but the technical architect must define a design for the collection, retention, and security of data within the web application itself that meets GDPR requirements.
So merely using native GCP services or enabling a console setting for data location is insufficient.
Correct. Compliance is a shared burden. The application design, how explicit user consent is handled, how data is collected and retained according to specific legal requirements, where it resides geographically, and most importantly, how a right-to-be-forgotten request is technically implemented, all that falls squarely on the user, the customer, and the architect, not the cloud provider.
The architect must proactively build data security and privacy by design into the application structure to meet GDPR standards.
By design.
Finally, let's hit the essential security rule for microservices. Secrets management. We have a large distributed application with 30 microservices all running in GKE, and they all need database credentials, API keys, and external tokens. Where should those credentials be stored securely?
The rule of thumb here is non-negotiable, and it applies across all cloud providers and architectures. The credentials must be stored in a secret management system. Whether the architect chooses Secret Manager, HashiCorp Vault, or another purpose-built solution, centralization and controlled access are paramount.
Why not the common developer shortcuts, like storing them in source code or even environment variables? They're easy to implement.
They're easy to implement and catastrophic to secure. Both methods expose the credentials. Source code ends up in version control history, creating massive, permanent leak risks. Environment variables are easily viewed by anyone with shell access to the host machine, breaking the principle of least privilege. But more critically, these shortcuts make rotation impossible without restarting every service and manually updating every single configuration.
It's a nightmare at scale.
It is. A dedicated secret manager centralizes storage, manages versioning, handles rotation automatically, and ensures access is controlled via IAM, granting credentials only at runtime to the service account that needs them. It's essential security hygiene for any distributed architecture.
Okay, so encryption is often called the last line of defense, but the strength of that line depends entirely on the security of the key itself. This brings us to key management systems, KMS, and the importance of hardware security assurance.
In high-security or regulated environments, think finance, health, or defense, there is often a mandatory compliance requirement for physical key security, specifically certification like FIPS 140-2 Level 3. This typically means the key must be protected inside a specialized, tamper-proof physical device.
But the whole point of the cloud is to abstract away the operational burden of managing physical infrastructure. Most users don't want the headache of managing physical servers, monitoring ambient temperature, and specializing in encryption hardware.
Of course not.
They want the security of a physical device, but the simplicity of Google managing the operational hardware.
That is the perfect architectural compromise and use case for cloud KMS with a hardware security module, or HSM. We need to define what an HSM is. It's a physical cryptographic device designed specifically to protect, store, and manage digital keys. It is built to be tamper-resistant and tamper-evident.
So by using Cloud KMS with the HSM option,
you get the FIPS S140-2 Level 3 certified hardware assurance. This means the encryption keys themselves are created within and never leave the highly secure certified hardware boundary. Google manages the physical security, maintenance, and availability of that hardware for you, but the cryptographic assurance is maximized because the key material is physically isolated.
So the key material never leaves the secure certified black box. That grounding in physical security is essential.
It's the highest level of assurance you can get in the cloud.
Let's pivot to another essential function of cryptography: message integrity and non-repudiation. We're designing a mobile chat application, and the crucial requirement is preventing message spoofing. We need cryptographic proof that a message was truly sent by a specific user. We need authenticity and integrity.
This is a classic challenge that requires us to shift from symmetric encryption, where one key locks and unlocks the data, to asymmetric cryptography, or public key infrastructure, PKI.
PKI relies on that key pair.
Okay.
A private key, which only the user holds, and a public key, which is widely distributed and known. How do we use that pair to prove a message's origin?
Instead of using the keys for confidentiality for encrypting the content so no one else can read it, we use them for digital signing. You use PKI to digitally sign to cryptographically process the message client side using the originating user's private key.
Wait, we use the private key for the signing process. If a private key is used to sign something, how does the public key verify it?
Think of the private key as the user's unique, personal, cryptographic seal or stamp. When you sign the message with the private key, you create a unique signature block or hash appended to the message. The recipient then uses the sender's widely available public key to verify that signature.
And if the verification works?
If the public key successfully verifies the signature, it proves two things. First, the message has not been tampered with since it was signed. That's integrity. And second, that it must have originated from the sole holder of the private key, the sender. Since the private key is held exclusively by that user, this cryptographic proof establishes the source beyond doubt.
So it solves the spoofing problem and achieves what's called non-repudiation. The sender cannot later deny they sent the message.
That's it, exactly.
Okay, we've built our robust IAM structure, we've secured our keys within an HSM, and we've cleaned our data using DLP. Now we need the final impenetrable wall around our most sensitive resources, ensuring that even if an identity is somehow compromised, our core data cannot be exfiltrated. This brings us to the expert level of control, VPC service controls, or VPC SE.
This is the layer that confuses people most because they often think, if I have IAM, why do I need VPC-SC? The distinction is vital. IAM manages who can access a service, the identity. VPC service controls manage where the data can go and from where services can be accessed.
The network and service boundaries.
Right. IAM is access control at the front door. VPC-SC is the impenetrable fence around the entire property that overrides the key holder's rights.
And that fence is called the service perimeter. Let's explore its power, specifically regarding preventing data exfiltration. Scenario 1. We have a user, let's call him an analyst, who has valid, necessary IAM permissions to read highly sensitive data in a BigQuery table within our project. But we need to ensure that user, even with their valid IAM key, cannot copy that data to a personal, non-corporate Google Drive or to a cloud storage bucket outside our organization.
This is the exact vulnerability VPC-SC was designed to solve. IAM alone cannot stop data exfiltration to external services because the user is authorized to perform the action of moving data.
So even though the user has the key, the IAM permissions, we use the perimeter to stop the escape route.
Correct. The solution is to implement a VPC service controls, a service perimeter, around the project containing the sensitive BigQuery data. This perimeter acts as a hard wall, blocking access to all services outside that perimeter, especially external, non-corporate services. If the analyst tries to run a command that copies data from BigQuery inside the perimeter to a Gmail account or an external bucket outside the perimeter,
The perimeter just stops it.
the VPC-SC control intercepts the request and blocks it completely, regardless of the valid IAM permissions the user holds.
That's a hard stop. It's fascinating how VPC-SC acts as a secondary, higher-level governance layer that overrides standard access permissions. It enforces a structural boundary over and above identity authorization.
It creates a true network and service boundary for the sensitive services, essentially isolating them from the public internet and external cloud services, even though they are technically being accessed via public API endpoints.
Let's take the combination one step further, synthesizing two expert concepts, using both network context and the perimeter. Scenario 2. Data analysts have IAM-read permissions, but security requires preventing them from retrieving data from those highly sensitive buckets when they are outside the trusted office network. They can only access it when physically at HQ.
We have to combine the service perimeter, VPC-SC, with the contextual enforcement mechanism we discussed earlier, access levels. This is the gold standard for layered security.
Walk us through the two steps to achieve this.
First, you create the VPC service controls perimeter that includes the projects with the sensitive buckets. This sets the hard boundary and prevents exfiltration to external services entirely. That's step 1. Second, you create an access level using Access Context Manager that specifically restricts access to that perimeter based on the CIDR range of the office network. Now, only requests originating from that trusted IP range are allowed to interact with the perimeter-protected services.
So if an analyst tries to access the data from home or a coffee shop,
the access level denies their request to interact with the perimeter, and the request fails instantly. This allows for granular, contextual policy enforcement at the service layer, guaranteeing that access is only granted when the identity and the network posture are simultaneously correct.
this entire deep dive has reinforced one critical lesson. Modern security architecture is entirely reliant on defense in depth or layered defenses.
It really is. We start with a foundational, well-structured IAM hierarchy that leverages the union rule and groups for efficient access management. We build upon that with specialized, targeted controls like Cloud DLP for sanitizing sensitive data and using tokenization instead of hashing when retrieval is required.
And we culminate with the hardest, most external layer.
Yes, VPC service controls, which draw an impenetrable perimeter around our critical services, overriding standard IAM permissions to structurally prevent data exfiltration.
It's clear that the who, IAM, and the where, VPC-SC, must work in tandem. For you, the listener, the key technical takeaways from today are understanding the essential difference between irreversible hashing and reversible tokenization, knowing that the IAM policy is the union of all inherited permissions, and recognizing that advanced controls like IAP combined with access levels allow for true zero-trust enforcement based on device state and location context. And architecturally, always remember that compliance like PCI or GDPR requires a bespoke design that minimizes scope and actively addresses the regulation, rather than just flipping an easy switch.
The technological toolkit is immensely powerful. We saw how workload identity federation eliminates the need for storing static credentials in cross-cloud scenarios, and how binary authorization enforces integrity at the deployment stage by demanding cryptographic attestations before execution. These are the tools that allow organizations to scale securely and meet their compliance goals without compromising velocity.
And here's where it gets really interesting. We started by noting that the most secure environments treat every single request, even from an internal employee, as potentially hostile until proven otherwise, verified by identity and contextual factors like device state and location.
Right.
But what happens when the next wave of identity verification moves beyond simply checking the device certificate and the source IP? What happens when systems start demanding continuous passive proof of identity based on biometric or behavioral analysis, keystroke rhythm, mouse movement patterns, or even gait to maintain continuous authorization?
A continuous posture check on the human themselves.
Exactly. If the system constantly monitors your unique human behavior to maintain a perfect, continuous situational awareness of who and where their users are, how much control are organizations and individuals willing to give up to maintain that level of perfect security assurance? That continuous behavioral verification challenge is the critical architectural and human challenge of the next decade in security.